what is natural production and how is it prevented from slowing? Natural production is the amount of oil recovered when a reservoir is first drilled. Deeply buried reservoirs trap gas, oil and water under very high pressure. Reservoirs are typically connected to the surface over great distances via aquifers. As water is more dense than oil, it exerts a greater pressure than an equivalent column of oil. So when it is first put on production, the pressure in the reservoir is greater than at the base of the oil well. This way, the fluids are naturally pushed to the surface. But over time, the reservoir pressure drops, until finally, it is the same as the pressure at the bottom of the well. When that happens, the well stops flowing. How is gas used in secondary oil recovery, and what limits it? Like water, gas produced with the oil from a reservoir can be re-injected to maintain reservoir pressure and keep production going. Gas is much lighter than water or oil, so it tends to gravitate upwards. This means it's better able to reach the upper layers of the reservoir, but poorer at reaching the lower layers. Additionally, gas being less viscous than water can be more effective than water in areas of lower permeability. In reservoirs with no extensive barriers to vertical flow and where there is a sufficient supply, gas can be used in a process called gravity drainage. Gas can be injected in the higher layers of the reservoir where it tends to stay as it is lighter than oil. With continuous injection, the gas layer starts expanding downwards as a stable front due to its density difference with the oil. Some of the oil is pushed to the producers, whilst oil behind the gas front continues to drain down, hence the name gravity drainage. Although gas can help increase recovery, in many cases the residual oil saturation from a basic gas flood is similar to that of water. So, gas alone cannot make much difference to the industry average of 35% oil recovery unless it interacts more with the oil or improves sweep.
On average, only 35% of oil is recovered from the ground, leaving around 2/3 behind. With demand for energy increasing by more than 30% by 2035, the world needs to produce more oil more efficiently from existing resources. We appear to have reached a point globally when the potential for enhanced recovery from existing resources exceeds the potential from new discoveries. EOR creates opportunities for lower cost production with less environmental impact. BP is the leading international oil company in the delivery of conventional oil production using EOR. The key challenge is implementing these technologies successfully in any margin environment.
BP's strategy for technology development in the EOR space is to develop technologies that are low cost, that are very widely applicable around the world and are readily deployable.
Our unique expertise in water injection EOR means we're the only company in the world currently deploying a low-sal EOR project. We are also exploring ways to improve efficiency of our water floods, specifically with a novel polymer technology.
Polymer actually attempts to change the physical properties of the water injection. So you add polymer, you can viscosify the fluid. That actually helps prevent the water from fingering through the oil. It also slows the water down that's shooting through high permeability streaks and layers in the reservoir, acts in a more piston-like displacement and therefore improves your sweep and gets more oil out of the ground.
The addition of polymer to water injection is not a new idea, but it has its own inherent problems that make it difficult to deploy.
Sometimes if you have to inject through a complicated injection system, you actually degrade the polymer. It goes through subsea chokes, for instance, and actually gets broken down.
Polymer chains are very long molecules and inherently weak to shear forces. It's the length of the polymer chain that actually adds viscosity. So if you chop up that chain into smaller bits, you lose a lot of your viscosity.
As a result, we've been collaborating with Nalco Champion on developing a reservoir-triggered polymer which has the ability, once applied to the water, to viscosify only when it is deep within the reservoir.
If you can add your polymer and it doesn't actually activate until it gets into the reservoir, then you have your cake and eat it.
The long polymer chain is constrained into a ball. Within that ball, holding it together, are stimulus-responsive bonds designed to react or trigger by temperature. The region around the well bore is well swept with water. It's going to be a lot cooler. Once it reaches what we call the thermal front, deep out in the reservoir, the bonds start to trigger and the polymer can unfurl and viscosify the fluid.
Together with Nalco Champion, we've developed and bench-tested this new polymer technology, and it has now been field trialled to prove it behaves as intended at field scale.
Before we invest in any technology, we need to demonstrate very, very clearly in a reservoir that it does what it says on the can.
So what we're looking for in this trial first is how does it inject, the pressure that it's going to inject with in comparison to water? And second, do we see that triggering event and are we able to produce the polymer at the producing well with the viscosity that we expect?
The field trial has been successful. The polymer was injected without being degraded, with minimal impact on injectivity, and subsequently activated deep within the reservoir.
We were able to take a downhole sample in our production well that showed the viscosity of the polymer sample was the same as an unsheared reference sample that we had at surface. Additionally, we had the downhole gauge data in the injector, and this showed that as the polymer started to trigger, downhole pressure increased. Those same gauges also gave us data during a series of pressure build-up and pressure fall-off tests, and that allowed us to infer what was going on in the reservoir and to see the developing viscous polymer bank.
The success of the field trial is further proof of BP's leadership position in enhanced oil recovery and our commitment to recover more of the world's oil from existing reservoirs.
As far as we're concerned, if we can develop viscosity of the water in the subsurface, then we're going to get incremental oil.
It actually will benefit most of our water-flooded reservoirs. There's widespread candidates across our portfolio that could use this technology.
Similar to how steam or water flood with polymer injection stimulates reservoir production, Chevron also uses gas EOR technology to help hydrocarbons flow more easily to the well. After first injecting water into the reservoir, our engineers pump carbon dioxide or hydrocarbon gas through the same injection wells. The gas mixes with the trapped oil, causing the oil to expand and dissolve from the reservoir rock, creating a miscible zone that allows the oil to move more easily to the well and be produced. Normally, gas injection is alternated with more water injection, and the water acts to sweep oil toward the production zone.
Canada's oil sands are recovered using two main methods: drilling and mining. About 80% of the resource, known as bitumen, is found between 100 and 800 meters below the Earth's surface. These reserves are too deep to be mined and are recovered in place, or in situ. One of the in situ methods is called steam-assisted gravity drainage, or SAGD. Found in formations consisting primarily of sand, the bitumen is located beneath a layer of hard rock called cap rock. In SAGD, steam is used to warm the bitumen so it can be pumped to the surface. The operator drills a pair of wells that sit one above the other in the formation. The top well is called the injection well. The bottom well is called the production well. Steam is injected into the top well. The steam moves into the formation, warming the bitumen. With the help of gravity, the bitumen flows to the production well, along with condensation from the steam. The bitumen and condensed steam, or water, are then pumped to the surface. The bitumen and water are sent by pipeline to a central processing facility for separation. The water can then be recycled, converted to steam, and sent back to the well site to be used again in production. Bitumen is a valuable resource that can be refined into transportation fuels such as gasoline, diesel, and jet fuel. It can also be used by petrochemical plants to create everyday products like cosmetics, textiles, plastics, and lightweight construction materials. Learn more at cap.ca.